The International Prize in Statistics stands as a beacon of excellence, a monumental honor often hailed as the Nobel Prize of its field, reserved for those whose contributions redefine how we understand the world through numbers. To claim this prestigious award, one must deliver a breakthrough so profound it reshapes the very fabric of statistical science, with ripples felt across disciplines, from technology to human welfare. In 2025, this coveted prize was bestowed upon a visionary whose work on smoothing splains ignited a revolution in data analysis, transforming the way we extract truth from chaos. This script unveils the electrifying story of that idea, an idea so powerful it's been called the backbone of modern machine learning, a game changer that's rewriting the rules of science and society. Buckle up for an emotional, jaw-dropping journey into the heart of a statistical masterpiece that's changing lives, one calculation at a time. Picture a world drowning in data, billions of numbers, signals, and observations flooding in from every corner of existence. Weather patterns shifting unpredictably, medical scans revealing hidden truths, financial markets pulsing with volatility. In this chaos, how do we find meaning? How do we separate signal from noise? The answer lies in a concept so elegant, so revolutionary, it's been dubbed the mother of all data solutions. Smoothing splines, the brainchild of a trailblazing mind, emerged as the key to unlocking patterns in noisy data, offering a lifeline to scientists, engineers, and dreamers alike. But what are smoothing splines, and why are they the talk of the statistical world? Let's dive into the heart of this mind-blowing discovery, a story that's as inspiring as it is transformative. Imagine you're a scientist staring at a scatterplot of data points, each dot representing a measurement, a moment, a truth obscured by randomness. Your predictor, let's call it X, could be time, temperature, or even a patient's blood pressure. Your outcome, Y, is what you're trying to predict. Rainfall, disease progression, or stock prices. The relationship between X and Y is governed by some mysterious function, but it's buried under a fog of noise, a pesky epsilon term that distorts what you see. Your mission? Uncover that hidden function, the truth beneath the chaos, and use it to make predictions that could save lives, protect ecosystems, or revolutionize industries. Sounds simple, right? Wrong? This is one of the toughest challenges in statistics, a puzzle that's baffled minds for decades. Now, if you've ever dabbled in statistics, you might think of linear regression as the go-to tool for modeling relationships. It's like drawing a straight line through your data points, assuming the connection between X and Y is tidy and predictable. Linear regression is a workhorse, reliable, straightforward, and built on just a few numbers, those trusty regression coefficients. Once you estimate them, you've got your model, ready to predict. But here's the catch. The real world isn't always so neat. Relationships in nature, in society, in biology, they're often curvy, complex, and anything but linear. Assuming a straight line when the truth is a winding path is like trying to navigate a maze with a ruler. It's a simplification that can lead you astray, missing the nuance, the beauty, the reality of the data. So, we step back to a more general model, one that doesn't force a straight line, but allows the relationship between X and Y to take any shape. A function, infinitely flexible, infinitely complex. This is where things get wild. Functions are what statisticians call infinite dimensional objects, meaning they can take on an endless array of forms. Estimating a function is like trying to map every star in the sky with a pencil. If your predictor X can be any real number, say between 0 and 1, there are infinitely many possible values it can take, and thus infinitely many values the function can produce. To reconstruct that function, you'd need to estimate an infinite number of points, a task no supercomputer, no matter how powerful, could ever handle. This is the heart of non-parametric statistics, a realm where traditional methods falter and the stakes are sky high. Let's make this concrete. Suppose you've collected a data set with n pairs of observations, each pair an x and a y, like snapshots of reality tainted by noise. Your goal is to estimate the function, let's call it f hat, that best captures the relationship between x and y. Done right, f hat will let you predict y for any new x, slicing through the noise to reveal the underlying truth. But how do you define f hat? The classic approach is to find the function that minimizes something called the penalized least squares criterion, a mathematical balancing act that's as elegant as it is powerful. This criterion has two parts, a least squares term and a penalty term, each pulling in opposite directions to create a perfect harmony. The least squares term is familiar to anyone who's run a regression. It demands that your estimated function, f hat, stays as close as possible to the observed y values. It's about fidelity to the data, ensuring your predictions hug the truth you've measured. But here's the problem. If you only minimize the least squares term, your function will cling too tightly to the data, chasing every random wiggle and quirk. The result? A jagged, overfitted mess that's great at predicting the data you already have, but useless for new observations. It's like memorizing the answers to a test instead of learning the material. Impressive in the moment, disastrous in the long run. That's where the penalty term swoops in, like a wise mentor guiding a reckless student. This term is a functional, meaning it takes your function as input and spits out a number that measures its wiggliness. The rougher, wavier, or more erratic your function, the higher the penalty. One common penalty is the integral of the squared second derivative of the function. A mouthful, sure, but it's a brilliant way to quantify smoothness. Wiggly functions have wild second derivatives, so this integral skyrockets for overly complex models. By adding this penalty to the least squares term, you force f hat to strike a delicate balance. Close enough to the data to be accurate, smooth enough to generalize to new data. It's a tug-of-war between precision and elegance, and the winner is a function that's both predictive and beautiful. But there's one more piece to this puzzle. Instead of searching for any old function, we often restrict our hunt to a specific family of functions, a function space defined by shared properties. Think of it like choosing a genre for a movie. You could pick a space where functions are absolutely continuous, with derivatives up to a certain order that behave nicely and whose higher derivatives are square integrable over a given interval. Don't worry about the jargon. The point is, you're narrowing the playing field to functions with desirable traits, making them the search for f hat more manageable. This choice of function space is critical, setting the stage for the magic that's about to unfold. Now here's where the story gets electrifying. Even with this setup, penalized least squares, a carefully chosen function space, we're still stuck. We've defined f hat mathematically, but we don't know what it looks like. We can't evaluate it at a specific x to make a prediction. It's like having the recipe for a perfect cake, but no idea how to bake it. This is the wall that statisticians hit for years, a problem so daunting it seemed insurmountable. Enter the genius of smoothing splines, a breakthrough so profound it's been called a statistical miracle. In a seminal 1971 paper, two brilliant minds published a result that turned this impossible challenge into a solvable one, a result known as the representer theorem, a name that echoes through the halls of statistical history. The representer theorem is a game-changer, a lightning bolt of insight that transforms an infinite-dimensional nightmare into a finite, manageable problem. Here's the gist. The function that minimizes the penalized least squares criterion can be written as a linear combination of special functions called kernels, one for each observation in your dataset. Instead of estimating an infinite number of points, you only need to estimate n coefficients, those betas, just like in linear regression, but now they're working with kernels instead of raw predictors. These kernels, denoted as k, are the secret sauce, magical functions that capture the essence of the data's structure. The theorem says your f hat is a sum of these kernels, each weighted by a coefficient, creating a smooth predictive curve that dances through the noise. Let's break this down because it's too incredible to rush through. Suppose you have n data points, n pairs of x and y. For each observation, you create a kernel function centered at that x value. These kernels live in a special place called a reproducing kernel Hilbert space, a mathematical wonderland with properties that make our lives easier. A Hilbert space is a function space equipped with an inner product, a way to measure how similar two functions are. The reproducing part means that these kernels have a superpower. If you take the inner product of a kernel with any function in the space, it's as if you evaluated that function at the kernel's corresponding x value. This property is what makes the kernels so powerful. They reproduce function evaluations, turning abstract math into concrete predictions. To estimate f hat, you choose a kernel, say the Gaussian kernel, a popular choice that creates smooth, bell-shaped functions. According to the representer theorem, your estimated function is a blend of these n kernel functions, each one anchored to an observation and scaled by a coefficient. Instead of grappling with infinity, you're now solving for n numbers, a finite, computable task. By minimizing the penalized least squares criterion, you find the optimal coefficients, and voila, you've got f hat, a smooth function ready to predict y for any x. It's a breathtaking leap, a moment where mathematics bends reality to our will, making the impossible possible. Let's visualize this to feel the awe. Imagine a true underlying function, a green, curvy line representing the real relationship between x and y. Now you observe three noisy data points, red dots scattered around this curve, each slightly off due to random noise. Your goal is to reconstruct that green curve using only these red dots. Using the representer theorem, you take each red dot's x value and plug it into a Gaussian kernel, creating three smooth, bell-shaped functions. These kernels are like building blocks, and the theorem tells you to combine them in a linear combination, tweaking the coefficients to get the best fit. As you adjust those coefficients, the combined function morphs, curving and bending, to hug the red dots while staying smooth and graceful. The result? A curve that's eerily close to the true green function, a triumph of mathematics over noise. This is the power of smoothing splines, a method so versatile it's been applied to everything from climate science to medical imaging. In climate studies, smoothing splines analyze spatial patterns in global temperature data, revealing trends that guide policy and action. In medical imaging, they enhance image reconstruction, sharpening blurry scans to help doctors diagnose diseases. In machine learning, they underpin kernel-based algorithms like support vector machines, driving innovations in artificial intelligence that touch every aspect of our lives. This isn't just a statistical tool, it's a revolution, a paradigm shift that's redefined how we see the world. But the story doesn't end with the representer theorem. The genius behind smoothing splines didn't stop there. Another seismic contribution was the development of generalized cross-validation, or GCV, a method that solves a critical practical problem: choosing the smoothing parameter. That penalty term we talked about, it's controlled by a parameter, often called lambda, that dictates how much weight to give smoothness versus fidelity to the data. Too much smoothing, and you oversimplify the function, missing key patterns. Too little, and you overfit, chasing noise instead of truth. Finding the right lambda is like tuning a guitar. Too tight or too loose, and the music falls flat. GCV is the answer, a brilliant technique that automatically selects the optimal lambda by simulating how well the model predicts data it hasn't seen. It's like having a crystal ball that tells you how your model will perform in the real world. By minimizing the GCV criterion, you find a lambda that balances smoothness and accuracy, ensuring your smoothing spline is both predictive and robust. This innovation made smoothing splines practical, turning a theoretical triumph into a tool that scientists and engineers could wield with confidence. It's no wonder GCV is now a cornerstone of statistical practice, used in everything from data mining to predictive modeling. The impact of smoothing splines is staggering, a testament to the power of a single idea. They've been generalized to countless applications, from multidimensional predictors to exotic loss functions, each adaptation pushing the boundaries of what's possible. In machine learning, they've birthed algorithms that power self-driving cars, voice assistants, and recommendation systems. In climate science, they've helped model complex systems, predicting everything from hurricanes to ice melt. In medicine, they've improved diagnostic tools, catching diseases earlier and saving lives. This is the kind of impact that earns the International Prize in Statistics, a recognition of work that doesn't just advance science, but reshapes the world. Let's pause for a moment to feel the weight of this achievement. The 2025 winner didn't just solve a math problem, they changed how we understand reality. Their work began in the 1970s, a time when computing power was a fraction of what it is today. Yet, their insights laid the foundation for the data-driven age. They pioneered non-parametric regression, practicing data science before the term even existed. Their methods have stood the test of time, remaining a mainstay even as machine learning giants like neural networks and gradient boosting dominate the headlines. This is a story of perseverance, of vision, of a mind that saw beyond the horizon and brought the future into focus. The emotional resonance of this story is undeniable. Imagine dedicating decades to a field that's often misunderstood, toiling in the shadows of flashier disciplines like physics or computer science. Statistics isn't always glamorous. It's the unsung hero, the engine behind every major discovery. Yet this winner never wavered, driven by a passion for truth, a belief that numbers could reveal the world's secrets. Their journey wasn't easy. As a trailblazer in a male-dominated field, they faced skepticism, barriers, and countless challenges. But they persisted, shattering glass ceilings and proving that brilliance knows no bounds. Their story is a beacon of hope, a reminder that one person's vision can change the world. Now let's zoom out and see the bigger picture. The International Prize in Statistics isn't just about one idea or one person. It's about the power of statistics itself. This field, often dismissed as dry or esoteric, is the backbone of modern society. It's how we test vaccines, predict elections, and fight climate change. It's how we make sense of a world that's messy, uncertain, and overflowing with information. The 2025 prize shines a spotlight on this truth, reminding us that statistics isn't just numbers, it's stories, it's lives, it's the future. The legacy of smoothing splines is still unfolding, a ripple effect that's touching every corner of human endeavor. In education, they're helping analyze student performance, identifying gaps and tailoring interventions. In finance, they're modeling risk, protecting economies from collapse. In public health, they're tracking pandemics, guiding policies that save millions. Every time you use a smart device, benefit from a medical breakthrough, or marvel at a weather forecast, you're touching the legacy of smoothing splines. This is the kind of impact that transcends generations, a gift to humanity that keeps on giving. But let's get real for a second. This isn't just about equations and algorithms, it's about people. It's about the scientist who stays up late, wrestling with data to find a cure. It's about the engineer who uses these tools to build a safer world. It's about the student who discovers statistics and realizes they can change the world. The 2025 International Prize in Statistics isn't just a trophy or an $80,000 check. It's a celebration of human ingenuity, of the relentless pursuit of truth in a world that's anything but certain. As we wrap up this journey, let's reflect on what makes this story so electrifying. Smoothing splines aren't just a method, they're a philosophy, a way of seeing the world. They teach us that truth is often hidden, buried under noise and complexity, but with the right tools, we can find it. They remind us that progress isn't always loud or flashy. It's often quiet, meticulous, built on decades of hard work. And they show us that one idea, born from one mind, can spark a revolution that touches billions. So what's next? The world of statistics is evolving faster than ever, fueled by advances in computing, artificial intelligence, and big data. Smoothing splines are just the beginning, a foundation for the next wave of discoveries. The 2025 prize is a call to action, a challenge to the next generation of statisticians to push the boundaries even further. Whether you're a student, a scientist, or just someone curious about the world, this story is for you. It's a reminder that you too can make a difference, that your ideas can shape the future. Let's end with a vision. Imagine a world where data isn't a mystery but a map, guiding us to better decisions, stronger communities, and a brighter tomorrow. That's the world the 2025 International Prize in Statistics is building, one spline at a time. This is the idea that won the Nobel Prize in Statistics, not just a mathematical triumph, but a human one, a story of courage, brilliance, and hope. Thank you for joining this journey. Let's keep exploring, keep questioning, and keep chasing the truth together.